When we model a real object as something other than a mathematical point, we can show the forces acting at their actual points of application. Then we must look at how applying forces at different places affects the object. The basic effect of forces applied at different points is to cause the object to twist or turn. Think about how your hands on a steering wheel cause the wheel to turn, or how a hand on a wrench can tighten a nut on a bolt. Using the rigid body model allows us to establish a way to measure this twisting effect. The quantity that measures the tendency of a force to cause rotation is called torque, and is given the symbol tau. In each of the cases, the object shown in the diagram is acted on by one or more forces. All diagrams are in a vertical plane so that the Earth is down in the diagram and the sky is up. The object is shown in the first box. Click on the points of the sketches where forces are acting on the object. This arrow represents each force and indicates what caused the force. In the second box, you see a rigid body force diagram with appropriate labels for all forces. Notice that if you had distances or weight values that you could easily pick any single point of rotation and write down equations that sum the total amount of clockwise or counterclockwise torque. In the previous part of the lesson, you should have discovered that the larger weight must be closer to the pivot point than the smaller weight in order for the seesaw to balance. Mathematically, these two quantities must be in an inverse ratio to each other for the balance condition. Let W sub 1 be the large weight and W sub 2 be the small weight, while R sub 1 is the large weight's distance from the pivot, and R sub 2 is the small weight's distance from the pivot. This mathematical relationship is then expressed like this. The object has one condition for equilibrium verified, that being that the torques are balanced. Additionally, we could write Newton's second law equations in the x and y direction and show that they are also balanced. Hence, this object is in a state of static equilibrium. Here's an example. A weight of 10 newtons is placed on a model seesaw a distance of 30 centimeters from the pivot. Where should a weight of 20 newtons be placed to balance the seesaw? Using the torque equation, we get this equation. There is one more factor that must be taken into consideration when looking at the torques on the seesaw. If the 10 Newton weight in the example was the only force acting on the seesaw would rotate in a counterclockwise direction. Likewise, if the 20 Newton weight was the only force, the seesaw would rotate in a clockwise direction. Even though the direction of both forces is downward, the two forces acting on the seesaw are causing torques that would cause rotations in opposite directions. Because the torque has this directional aspect, we need a method of indicating the direction of rotation that any given torque will cause. The convention chosen by scientists is that any torque that will cause a counterclockwise rotation is a positive torque. The diagram shows a fishing pole attached to a support base on a boat. The fisherman exerts a horizontal force, F sub E, on the pole. If the fish has a weight of 11 newtons, what is the magnitude of the force F sub E exerted on the pole by the fisherman? Set this problem up using torques about the end of the rod. F sub E on the pole times 0.5 meters distance will provide one torque set equal to the quantity of 11 newtons fish weight times sine of 40 degrees times the 2.5 meters from the tip of the rod. In a rowboat, a person is using an oar. If the distance S sub E is 60 centimeters and S sub R is 180 centimeters, the force on the handle is 170 newtons. What is the resistance force F sub R? This is a lever problem where you have torques on either side of the fulcrum and they are set up to be balanced. Therefore, F sub E times 0.60 meters should equal F sub R times 1.8 meters. This should give approximately 57 newtons for the resistance force. In this example problem, a restaurant sign is attached to a wall by a pole and cable. The sign has a weight of 200 newtons and the uniform 1 meter long pole has a weight of 50 newtons. What is the tension in the cable and the horizontal and vertical components of the force on the pole from the wall? Step 1. Because the pole is supporting the sign, the pole is the object that must be kept in equilibrium. Draw a sketch on your own showing the situation. The sketch should look similar to the diagram. Steps 2 and 3. All contact points for the forces acting on the pole are identified on the sketch by circling them. The forces in this situation would be the weight of the sign, the tension from the cable, the horizontal and vertical forces at the wall, and the weight of the pole. Because the pole is uniform, we can assume that the weight acts at its center. The axis of rotation A is chosen to be the point where the pole is connected to the wall. This choice allows us to ignore the horizontal and vertical forces at the wall when summing the torques. These forces will, however, need to be taken into account when summing forces. Using the identified forces and contact points, a free body diagram is drawn. The diagram should show all forces at their points of application with the correct directions indicated. All appropriate distances are included on the free body diagram. So in step 4, a table of force, components, and torques about the chosen axis of rotation is constructed. Remember to take into account the direction of the torques and forces, and include signs as appropriate. The table for this example is shown here. Step 5. Apply the equilibrium conditions. Each column in the table corresponds to an equilibrium condition. The first column contains the x components. Adding the forces down that column and setting the result equal to 0 gives us this equation. Similarly, the second column represents this equation. The third column represents this equation. This result for the tension can be substituted back into the other two equations to obtain the values of H and V. Review this diagram. What is the tension in the cable and what are the horizontal and vertical components of the force that the hinge exerts on the crane boom shown here? The boom is 4 meters long. It has uniform density and its weight is 300 newtons. The weight, W, of the load is 2,000 newtons. Step 1 is draw a sketch. This would be the figure shown here. Steps 2 and 3. Because the crane boom is supporting the load, it is the boom that we want to keep in equilibrium. On your own, circle the points where forces are acting on the boom. These would be the hinge at the wall, the point where the horizontal cable attaches, and the end where the suspended weight is hung. The free body diagram shown indicates all the forces and weight of the boom. The axis of rotation is chosen as the hinge at the wall. This choice allows us to ignore the forces at the hinge when calculating torques, since they act at the chosen axis of rotation and will cause no torque through that chosen axis. However, those forces must still be taken into account when summing forces for the translational equilibrium condition. Solving the first equation gives T equals 3,610 newtons. Substituting this value into the second equation gives H equals 3,610 newtons. Finally, the third equation gives V equals 2,300 newtons. Step 4. In this table, the torques are written as products of forces and moment arms. The counterclockwise direction is taken to be the positive direction for the torques. Step 5. Since this is a static equilibrium situation, we want the boom to remain at rest. The sum of each column must be 0. Using this information, we generate the equations for the static equilibrium conditions. Step 6. Given the amount of weight being supported, the magnitudes of the forces seem reasonable. One useful feature of the torque condition for equilibrium is that you can change the axis A and check your work by using your calculated values for the unknown forces to determine the value of the sum of the torques about this new axis. If your values are correct, this new torque sum must also be 0. Try this for the calculated values of T, H, and V. If the new sum is not exactly 0, check to see if it is the result of using the calculated values that were rounded off to 3 significant figures. The problem-solving procedure illustrated in this example should be followed for all static problems. You should now be able to complete any assignments given to you by your instructor, including the capstone project problems in this course. This concludes this lesson. Do you now understand terms and concepts related to the physics ideas known as torque and rotational motion? In this lesson, you covered the following objectives.